So there's a couple of ways of, because of the, without replacement, the first and second picks are really not independent, but it's kind of interesting to think about that. So what the probability that the first one is green is more direct. If you randomly pick one of these boards, there's 2,000 that are green and 10,000 that aren't. So you get the 20% chance that the first one is green. What's the chance the second one is green? Well, there's one way to do it is to draw out a probability tree and figure out the chance that you get a second one that is green. We could look at that just, but there's a certain symmetry to it. Right? There's the first board and the second board. And you're picking a first board and a second board. And it's a little arbitrary which one is the first or second. If you had picked kind of the second first, and you don't really do that at the time, but kind of imagine it going the second one and the first one. Every pair that you get for the first and then the second one is you can get that pair for the second and the first and kind of reverse it. So it turns out the probability the second one is green is also 0.2. It's kind of a symmetry to those two things. But if you have that the first board is green versus the first one being okay, there's 2,000 out of the 10,000 are in this category, or you could write 0.2. And then there's 8,000 here and 10,000 for that. Once you get that, then the second one should be green. Or the second one should be okay for construction. And those two things can happen whatever you do for the first. But once you've picked one board, you no longer have 10,000. We have 9,999. 9,999 in every case. And depending on what you get at first, it affects what's left over at the second. So 9,999. And so if we pick the first one as green, how many green are left for the second? I have one less than that, that's 1,999. Or if we go this way, if the first one's okay, there's still 2,000 that are green. Right, so the probability of a green on the second is if you multiply these two things together and these two things together and then add them up, it does reduce down to 0.2 to get that probability. But so this one and some other, sometimes there's something to figuring out how to set it up in a tree, given the information, and whether you label different things. But is that?
Yeah, I just had a question on the last part.
What was that?
A union B.
Oh, A union B, that either one? That either one is green?
Or sorry, no.
A intersection B?
Intersect, yeah.
Right. So that would be that they're both green. Right? That, if they're both green, that's going to come down right through that channel. Right? The first one is green, and the second one is green. And in this case, I just put 2,000 or 0.2 out of 10,000 times the 1999 over the 9999, right? Which is not exactly 0.2 times 0.2. It's just a little bit different, right? Because what you pick your first one influences what's available for the second one, so they're not exactly independent. The mix changes what's available, so they're not exactly independent. But in this case, with 10,000, it's not much different, right? It's in the fourth decimal place or something. It's a little bit different, right? When it's only 10 boards, right, then there's a much bigger dependence, a much bigger effect, because taking out one is a tenth of the pool, so it changes things quite a bit more. So in this course, we cover a number of topics. Some descriptive statistics, a little bit about study design, and now some about probability. Part of the probability is reasoning along these lines and counting, getting some insights into how some of these things are done. The Statistics 251 is a probability course taught also in the spring, so next spring will be the next time, and it does this in a little more elaborate detail. Consider some other options. We've considered some discrete random variables, right? So binomial, geometric. So with our discrete random variables that we've looked at, we've looked at a general case. In the general case, we list our outcomes, and we give probabilities for those outcomes. You might give me a graph, might show a table, something to describe those probabilities. We might compute expected values. We might compute the standard deviation of the random variable to describe its variability. We saw binomial random variable, which is counting the number of successes out of n trials, whether they're independent, constant probability. N equals 1 is a special case called Bernoulli. Which is a 0 or 1 random variable. We had negative binomial. And that was called R and P. A special case of this one is when we had one success, and it was called geometric random variable. So again, you get a probability formula, expectation, variance formula, kind of the scenarios in which you would use these different things becomes important. We actually looked at a couple others, and for the first exam, eventually we might narrow this down to say which ones would be on the exam or not, just to limit formulas or provide something, because once you get more of these things, and there was Poisson with a certain rate that counted other things. And so these were all examples of different discrete random variables. They're not all of them. There's other special ones that you use in certain circumstances, but this probably covers 95% of the cases that actually would be out there. And all of these, they're counting discrete outcomes, 0, 1, 2, or something like that. And so this next homework that's due and posted correctly now asks some questions about these. Calculate the probabilities, look at the expected value, the variance of those from different formulas. And today we're really going to look at introduce continuous random variables. A lot of things that we measure or record are going to be more on an interval scale. So continuous random variables, the values we can see are in an interval. They're somewhere on the real line or the positive real line or the interval 0 to 1, something like that. They are, and so associated that we don't have a probability of a particular value because there's just too many of them. You can't enumerate them all, make them all a list of them. Instead, relative chances are expressed by either a cumulative distribution function typically referred to as a CDF, or as a probability density function. And the book that I learned this stuff from had CDF as capitalized and the PDF as a lowercase, and so that's what I tend to do. But the things that are measured in an interval, right, are things like, distance, time, distance, think length, area, volume of something. You might have an amount of time. You might measure concentrations in chemicals, parts per billion, essentially continuous, where you can get a lot of different outcomes. Some ratios get measured this way, like miles per gallon, or you can take a look at that, gallons per mile, right, and things like that. Sometimes dollars are put in this. Now dollars really don't exist on, there are pennies and dollars, so that you could argue, well, those things really are discrete, you can count all those. But if there's really a lot of levels of something, it is almost considered like, kind of an interval. So we might have a model that says it's essentially continuous, even though we know it's not really. Height or something might not be really measured to the micron level. It might be rounded to centimeters or millimeters or inches or something. But the underlying concept really is more continuous. Yes?
So with money, would it be something like stocks that would be considered random?
Yeah, so the stock price on a given day, you have where it is now. Is it going up? Is it going down? Right? And those change by the pennies. So essentially it's pretty close to continuous. Salaries, right? Home prices, rental prices for different things, all could be more continuous, right? Like that. So if X is a random variable, is a continuous random variable, the value that it can take on, the actual numerical value is we're going to represent by the lowercase f, right? The probability density function, or PDF, is going to be f of x, some function. A function is a probability density function if it's greater than or equal to 0 for all x. And if the integral over the whole real line of that density, right there, f of x dx is 1. We have a picture here, and that our density function is going to be something. It doesn't have to be completely regular or anything like that. But this height of this thing is f of x. It can go to negative infinity for some versions. It can go to positive infinity. Some others will zero out below 0. We only report positive values. And so this, the total area under the curve is 1. And probability is area between points under the curve. Right? So if we have 2 points here, A and B, right? The probability that our random variable, that our measurement we get, falls in that AB interval is going to be this area under the curve. So we would write that the probability that A is less than or equal to X is less than or equal to B is this integral from A to B of that density. And so for different curves, for different densities, their probabilities are going to change in that interval AB depending on their shape and how high they are there. If the values of x tend to be higher, you could have a curve that's shifted off to the right. You could have a curve that has most of its area in a narrower area, and that's going to change the probability of different occurrences. And a lot of the times we will give a specific form for f of x, like a normal density or something else, and in some cases you can actually calculate these densities, and sometimes it's going to be cumulative, right? So if you have one of those, that tells you about the random variable. The cumulative distribution function, or CDF, is the probability that x is less than or equal to a value. And this cumulative is defined the same way whether it's discrete or continuous. The probability that it's less than or equal to some value. Usually with the discrete ones, we only care about probability at the particular values that are possible, but it isn't defined the same way anyway. So this is going to be an integral from the lower point, whatever is possible, up to that x. So when x is up there, we're not going to write f of x in the expression, because there would be a little bit of confusion about which is x. So we usually put a placeholder in there. But it's the integral of the density. So say here's our density, here's a value of x. Right, the probability that x is less or equal to that is going to be this area to the left of it. So we can integrate that density function up to a certain point, we get the probability that it's less than that. And that's called the capital F CDF of that. So how do we express the probability that x is greater than some value? Well, we're just going to take the opposites, right? 1 minus f of x, which is 1 minus the probability that x is less than or equal to that value. In general. How about this one? The probability that a is less than or equal to x less than or equal to b. What is that in terms of cumulatives? Well, one thing to note before expressing this in terms of cumulatives, capital F, right, is that the probability for a continuous one at any point doesn't matter. Right? Continuous function, the probability that you're between 2 points and it's equal, is going to be the same calculation if it does not include the inputs. Right? The area under a curve at a particular point, right? There's 0 width at a particular point, where the actual point on the real line has infinitesimal dimension, right? It's just a point. So the probability exactly at this line under this continuous curve really is 0. So it doesn't, in this case, we're not too concerned. Is it greater than or equal to, and so on. That does matter for discrete ones, because there you have probability mass at certain points. So if you include one point or don't include it, it does make a difference. With the continuous ones, it doesn't. So that said, the probability you're between 2 points. So we have this picture here, and we have some values of A and B. And we want the probability that we're in above this, somewhere above that interval. And if I'm giving you the cumulative distribution function, whatever expression this is, to calculate the area in that strip, right? To calculate this area, we're going to take the upper point, right? Take all the area below it. But that's, of course, going to include too much, right? And that would include everything from here back below. But we can also apply that function to this, and then subtract out that what's left over, and we can get the, if we had the cumulative, without having to do the integral, if I had the f of x, capital F of x defined, I can just take that difference and get that. Now there's a relationship between the cumulative here's this one, the f of x, is that integral. So if I'm given the integral, this capital F of x, right, I can get back to this one. Right? I can take a derivative. So if I have an f of x, capital F of x, the cumulative distribution function, right, the density that's associated with that is just the derivative. So with respect to x of this f of x function. So you can go back between those. Right? And we'll do one other thing with that in just a minute. But let's look at an example. So in this case, let's look at an example here. A particular random variable is called the logistic random variable. There's lots of random variables with names that are used in different cases. One is called logistic random variable. It's a value, it takes values on the whole real line, so negative infinity to positive infinity are all possible for this one. Not all are likely, it's usually contained in a certain area. The cumulative distribution function f of x is given as e to the x 1 plus e to the x, for x an element of the whole real line. So the graph of that thing, of this cumulative, okay, here's the values of x. At x equals 0, I'll put a height over here off to the side. Well, these capital F of x's go between 0 and 1. So I didn't say that before, but the area goes up to 1 under the curve, right? And so f of x, as x goes towards infinity, is the area under most of the curve, and so it can't go above 1. As you go further to the left and you get less and less density, as you move further out, it goes towards 0. Right? This thing at x equals 0, the probability that x is less than or equal to 0 is e to the 0 over 1 plus e to the 0, which is just 1/2. So at 0 is at 1/2. And below 0, that probability is less. Above 0, it's more. So this thing comes out really slowly and then kind of sloops up and then kind of goes asymptotes. It's supposed to kind of look the same going both directions. Maybe a little curvier up there. So it kind of curves up and goes up. And it asymptotes at 1. It doesn't come up to 1. As you go further and further out, and eventually it reaches that. But at 1/2 is that. So the probability that x is less than, say, like with some number, is less than 2. Probably x is less than or equal to 2 is the cumulative distribution at 2. And if this is the random variable we have, it's e squared over 1 plus e squared. And that ends up being about 0.880. Right? About 80%, just calculating that in there. The probability that x is less than or equal to -2. Right, so up here. About here is 2 under this density. -2 is about here. This particular curve is symmetric about 0, right? So you go. So there's certain relationships here, but you can less than -2, e to the -2, 1 plus e to the -2, and that ends up being 0.1192, about 11 or 12%. This one's actually symmetric, so this one is actually is also the probability that x is greater than 2. Things are not always symmetric, they are, but this one turns out to be symmetric. So you can calculate different things that you are interested in.
with p-values?
Not directly, but p-values are probabilities under Taylor areas, right? So eventually we will have a t-distribution or a normal distribution and say what's the probability you're at a point or more under an area, right? So if this was kind of a reference distribution, a distribution for some test statistic, and we got a value of 2, a p-value, we might calculate the probability that we're at 2 or greater. So yeah, the Taylor areas under distributions, is where p-values come from. So eventually we'll see that. Right? So what's the 90th percentile? So what's the 90th percentile of a logistic random variable? So right now we have the CDF, which kind of goes like this. And the height goes from 0 up here to 1. This is the cumulative, and this is x. So what do you think we want to do to find the value of x that's the 90th percentile? Yeah.
You would just look at where f of x is equal to 0.9.
So here's 0.9. So what is f of x? F of x is the probability that x is less than or equal to a value. The 90th percentile is the value, the thing that is the 90th percentile is the value of x that equals that probability, right? So essentially we want to take this 90% and map it over here to the CDF value and then figure out what is the x value for that. Here's the 90th percentile. So we want, this was e to the x over 1 plus e to the x, setting that equal to 0.9. Right, that means that e to the x equals 0.9 times 1 plus e to the x. Or, let's see, there's 0.1 e to the x left on this side. If I subtract the 0.9, it equals 0.9. So e to the x equals that. 0.9 over 0.1, which is 9. So we need e to the x equals 9, right? So you take the natural log of both of these. In R, log by default is the natural log. So if you use the R program to take the log of 9, it automatically defaults to the natural log. And the natural log of 9 is 2.197. So if what we're measuring has a logistic distribution, 90% of the values are going to be 2.197 or less. What does the density look like for this? Right? This is the cumulative, kind of tells how things are increased, the probabilities are going as x is increasing. But we might want the density kind of at a certain point. Sometimes that's a little more, gives you another picture of the same random variable, right? So if f of x is e to the x over 1 plus e to the x, we want the density. All right, so we have to take a derivative of this thing, f of x. So this is a ratio of two things. So this is chain rule, or chain rule quotient rule, I guess it would be called. The derivative of this thing is 1 plus e to the x squared. And you take the first denominator times the derivative of the numerator, so that this one, the derivative of an exponent with no other multipliers or anything, is just that exponent again, e to the x, right? So we get an e to the x here again, minus the first term, the derivative of 1 plus e to the x is just e to the x, right? So the derivative of that one. So this is really what's going in here is that derivative. The derivative of this thing equals. That's really what's going in here at the end, is e to the x. And so in the numerator, you have e to the x plus e to the x squared, and this is e to the x squared, so you just get e to the x over 1 plus e to the x quantity squared. This is good for x on the whole real line. It's always good to keep track of where that density or the cumulative function works. Eventually we'll have some things that are only positive, so, yeah.
To make it slightly easier, couldn't you also do e to the x times 1 plus e to the x and negative 1?
You can, yeah, yep, yep. Yep, either way you want to do it. We will be doing a little bit, a few times these derivatives and a few integrals. All right, we don't spend a lot of time or do a lot of things. Things often involve polynomials, like x squared, x cubed, 1 minus x squared, or e to the x, or e to the beta x, or e to the negative beta x. So there's a few cases that come up a lot in doing this. Right. It's not a full review of all of those, but if you have a calculus book or an online list of derivatives for some common cases, that as you're seeing one, if you don't quite remember how to do it, you might be able to look up a few of those cases, or find other examples in the book where they do some things like that. We don't do a whole bunch, but to actually do this, it does involve calculus, and that's why we have some calculus requirement for this. That is a density function. This thing looks kind of bell-shaped. It's a little bit different than the normal curve, but again, it's kind of a symmetric curve. This is fx. And it looks something like that. Based on what we know about the cumulative, there's a lot of the probability, about 88%, 48.08 was the probability we were less than 2, whereas the cumulative distribution at 2, or the probability that x is less than or equal to 2. And there was just a little bit above up here. So if you try to draw it to scale, you would include a lot of the area, about 10% above or something like that. But that's what the density is actually symmetric. E to the x, 1 plus e to the x squared actually should equal e to the negative x, 1 plus e to the negative x squared. So if you multiply the numerator and denominator by e to the x squared, u to 2x now. 2x, right? So that's 1. If you multiply this one times this, the numerator becomes just an e to the x. So, yay. Right. And then one of these comes in here and it becomes another equation. So this is actually symmetric. Symmetrics. About 0 density, so we kind of equal likelihood in intervals down here as above here. Not all of them will be symmetric. We'll have some that are skewed. It works out for this one. Yeah.
This isn't the actual bell curve though, right?
This is not the actual bell curve. It's just a little bit different. There's another thing that is kind of a similar shape, right? But just as another example. Let's look at another example. One that's used in some applications is called Rayleigh distribution. Again, there's a lot of these things that are named that get used in special versions of engineering or physics or other things. The cumulative distribution for this one is 1 minus e to the negative x squared over 2 when x is greater than 0, and it's 0 otherwise. So this is a positive random variable. Where the only probability occurs, the only density or likelihood ever occurs on positive values. So things that are restricted in nature to be positive, you know, time or weight or something. Right? Wind speed would be positive. This thing kind of looks like, kind of goes up like this and kind of goes down. That's the density. So we better figure out what that is. And it's 0 back here. So I jumped the gun by drawing that graph. The density, so we want to take the derivative of this thing. Right, so this really will be an application of the chain rule. Because it's e to a power, so you can take the derivative of e to something, and then take derivative of the thing that's in the power. Get the density. Well, the 1 and doesn't, right, so we're going to get a negative e to the negative x squared over 2, but then we have to take the derivative of what's inside. And the derivative of what's inside, the negative is there, negative 2x over 2. So the negatives cancel and the 2's cancel, so we get x e to the negative x squared over 2 for x greater than 0. This thing is flat at 0, so a derivative there would just be 0. There's no probability accumulating until 0. So the density is 0 for x less than or equal to 0. So this particular function happens to have a graph like this. And so these small values of x have more probability. But there is this tail that has some probability stretching out. For some large values it would be possible, kind of a long tail distribution. Sometimes we can go the other way. Right? So one way, going the other way, uniform random variable between 2 points. The density for this is just going to be constant in the interval a to b, 0 otherwise. Special case is when this is uniform on this, uniform on, I call it u, call this random variable u. It's uniform on in just 0 to 1 and 0 otherwise. So we need to know what this constant is in here for our density. What's required of our densities? We need some positive numbers, so right, some positive density can't be negative. The other thing that to make it work out, we need it to integrate to 1. So whatever that constant is in there between a and b, it has to integrate to 1. That integral is cx, which is a constant times x, evaluated at x going from at b minus at c, so it's cb minus ca, or c times b minus a. And that thing has to equal 1. If we choose our constant right. So what's our constant? How high should our density be? I was going to say our density then has to be 1 over b minus a. So this constant here is 1 over b minus a. In our density function, for this uniform one, it's f of x, at a and b, there's just a constant height here, just a square rectangle where the height here in this box is 1 over b minus a. In this case, where it's just an interval of 1, the height is just 1. Maybe not the most interesting random variable, but probably the most useful. Because computers can generate, have algorithms for generating things that look like random noise, random 0, 1, random variables, and then they get transformed into other things. The other thing that we can do with this is figure out what the cumulative distribution is. So sometimes we can do, we have the density, what is the cumulative distribution? Well, if the density is 0 for x less than or equal to a, and then it's 1 over b minus a for in that interval, and then it becomes 0 again for b greater than equal to, for x greater than equal to b. We want to get the integral of this thing as you go along. And so f of x is essentially going to have 3 parts, right? Until we get up to a, nothing happens. We never see any observations, no probability. So it's still 0 if x is less than or equal to a. What's the cumulative once we get to b? What's the probability that we're less than or equal to some number if what we're looking at is beyond b? So if we have this is our density. If all of our relative probability happens in this area, we get past that cutoff. We've seen all the possible values, right? We're bigger than everything that's possible. So that cumulative is going to be 1. So it's going to be 1 if x is greater than or equal to b. In the middle there is where the integral really is going to, we can calculate the integral. So let's take some number x that's in this interval of a to b. Right. What's the probability that x is less than or equal to that little x? What's the little x here? Well, because of where the density is defined, that it's 0 below a, we're just going to calculate from 0 up to x, or a up to x. And we put our density in there, our f of x. Here is 1 minus b minus a. That thing in there is density. Dx. A is getting too long. So that's just a constant. So the integral is just a constant, is that constant times x. 1 minus. I'll do a d, I'll put a little t here for a placeholder, okay? That, I don't want to get x's confused, so if one of the limits is x, you put another letter in there to make it less confusing. So 1 minus b minus a, that thing times t. That's evaluated at t equals a and x. This is how I learned how to do these things. So we have 1 over b minus a, and you put it in first as x, minus, and you put that t in there as a. And so that's x minus a over just b minus a. This thing here is supposed to move over there. That's the cumulative function, cumulative distribution function, the CDF, for this uniform as you go to 0. What does that graph look like? If you go along to a and you're at 0, it's cumulative at this time. And then this thing is just a linear increase. As x gets bigger than a, just increasing at a certain rate. Until it hits b, and by that time this is all the way up to 1. And after that, it's just 1. So there's just a linear increase in the cumulative transformed into that constant rate, the constant uniform distribution there. So sometimes you can go from a density function and integrate it and get a cumulative. Sometimes we go the other way. We have a cumulative when you go back. Right? So these are a couple examples of random variables that are out there. But there's a whole bunch of them. And one place that they're described is in this engineering statistics handbook right here. So there's this engineering statistics handbook. Under this first chapter of Explore, there's a section on probability distributions down here. Right. And what is a probability distribution? Right. Here's a discrete one with probabilities. Here's a continuous one with the densities like we're doing. Right. Related probability functions, densities, CDFs are kind of defined there. Finding the percent points right, for one of these. And then it gives this gallery of distributions here, so some common ones. There's normals, T's, Cauchys, there's a number of things that are kind of symmetric that are slightly different from normal. There's some that are skewed, and so on. And the ones that we've talked about aren't there. They're kind of like this Weibel's pretty close to it, but there's some extra parameters in there. Was there a Rayleigh distribution? I don't see that one, log normal. Anyway, there's some different examples there. There's a couple discrete ones that they give as special cases that might be relevant that we've talked about. Right. The point of showing this is that there's some other resources out there. The cumulative percentile points for these. And there's a few other summaries that get used in other applications of these. Right? Another place to see some distributions is simply Wikipedia. Right? Now the issue with Wikipedia is that it's their presentation of it. Somebody's put that in, and it's not necessarily, you have to be careful with it. Right? They might choose a different way of writing things. This one has an extra parameter than we've had before. It has a scale. Right? We had sigma squared equals 1, but here's a cumulative. We had x, e to the negative x squared over 2. They have this extra parameter. Sometimes things get scaled, mean shifted, so sometimes things get changed. But they give some pictures. Wind velocity is one example. This gets used in some applications. Some different pictures depending on how you change the parameters and scale, and some other summaries. Yeah.
So I was just curious about one of the particular applications, but
Oh.
it's not really relevant.
Okay. But anyway, so this could, some distributions have other pages that describe things that can kind of be interesting and show some different things. One thing they do describe, the PDF, CDF is here, quantile functions. And they also do some things with mean and median and so on, and variance. Right? We're going to look at some of these. But as you encounter these possibly in application or possibly in a model, if it's not covered in our particular book, either this or some other sources might cover, describe it for you. Right? And so besides looking at the density, the PDF, so we have x as a random variable, we can look at the probability density function, f of x. We can look at the cumulative distribution function, capital F of x. We could figure out some percentiles. We could look at graphs. And those things will tell us about, you know, for that random variable, what type of values you're actually likely to see. Right? Does it look like the distribution if you had a big sample of values? Would it look like that density graph? The other thing we can do is look at expected value, or average value of a random variable. And for continuous random variable, the expected value. Now for a discrete one, we took the values times their probabilities and added that all together. We took a weighted average of those. But here it's continuous. So we take an integral over all the whole real line of values of x times its density. And so the potential values are weighted by that relative density over the whole real line. Now in most cases, the density decreases as you get towards the tail. Right? So even though the x's are infinite, the tails become arbitrarily small. And they become small fast enough that that's a finite integral. There's a few cases where it doesn't work, but that's another story. So in the case of uniform, say u is, we'll keep with x. The x is uniform on some integral. We figured out that the density of x is 1 over b minus a on for x in that little interval and 0 otherwise. Elsewhere. What would you think is going to be the average value of x if it's uniform between 2 points? Right? Probably someplace right in the middle, right? So if you take the expected value of x, it says to take the integral over the entire real line, right? But the density is 0 outside of that interval, so that's going to zero out its contribution. So where it's non-zero, we take the integral. And then it's x times the density, 1 over b minus a dx. The 1 minus b minus a is our f of x portion in there. This is probably the simplest case because the density is constant, but you would follow the same pattern. So integral of x squared, x squared over 2, and b minus a continues. Now x is evaluated at a and b. So we get b squared minus a squared over the 2 b minus a. But b squared minus a squared factors. Right, b minus a times b plus a. There's a 2 b minus a. So this b minus a cancels in both parts. And so our mean is just the b plus a over 2. On f. It'll get more complicated. We'll do some more examples where involved, a little bit more involved in doing the intervals. But we won't do a lot of craziest ones. But any questions about? So with the picture of our uniform, we're going to generate values. All our values of x are going to be between a and b, and they're going to occur with basically uniform frequencies in there. Right? So take the average of those. It's pretty much right in the middle, which is b plus a over 2. How about the variance? Variance and standard deviations of random variable. So the variance of x is the expectation of x minus its mean squared. The expectation of x using this notation that it's a mu or average. Like in theory. this thing would say to take the integral over the whole space of this function. When you take the expectation of a function, you take that function and you weight it by the density. So x minus u squared times the density times dx. Or whatever it is. That's the variance of a length variable. So it's the difference between the values you can have minus its mean, right, squared. And you weight it by whatever the density is. And this is done as an integral because of the continuous nature of the variable. That's fine. You can write that out and do it. Or the variance, because you can expand this, right, ends up being like this. You take the expectation of x squared minus what you got before as the mean, that thing's squared. So it would be a little easier to work these things out if you do it that way. Do all this calculation to find the expectation of x squared times its density. Figure out what that is and subtract the mean squared. Right? They're equivalent, but this one is pretty easier, often easier to do with calculus. How about the uniform? What do we get for uniform? What is expectation of x squared? So an integral, I'm going to restrict it to a to b because the density is positive only in that interval. 0 everywhere else, right, knocks it out. X squared, and the density is 1 over b minus a. That's x. So you get x cubed over b minus a, where x goes from a to b. So b cubed minus a cubed over b minus a. And again, a b minus a goes into factors into that, conveniently. B squared plus ab plus a squared. That times b minus a gives you that term. Isn't that nice? Right? So the variance is the expectation of x squared minus the expectation of x, that whole quantity squared. So you're going to get a b squared plus ab plus a squared minus, this was b plus a over 2, that term is squared. Oh, you know, b minus a, that's it, that's all there is. This thing ends up with a little bit of rearranging. B minus a squared over 12. Yes.
Does the factor of 1/3 cancel somewhere? I'm just not seeing from the integration.
Oh, integration, I forgot it.
Okay.
The 3 should continue. There should be a 3. That's where we're getting the 12, right? Thank you very much.
I did.
Yeah, so being careful with all those things is something to get used to again, right? But yeah, no, that's important. You need that 3 because here you have the factor of the base of 4, the 2 squared. You need a 3, combine it, you get 12. And it turns out to work out right, that way. Yeah. Exactly. So that's what it ends up being. So the 12, you know, I don't have I wouldn't expect you to sense that it's going to be 12. You know, where did that come from? And that's how it works out, right? B minus a over the square root of 12 as a standard deviation for our random variables. Right? And so that's generally kind of the introduction, right? These are continuous things. Right? We have a density or a cumulative. You could get percentiles. Right? We can calculate means, standard deviations. We're going to look at a couple primary examples of this. Right? One, we'll look at the normal distribution because that's a continuous one. I'll also look at something called exponential. We have something else called beta. That's a different variable between 0 and 1. So we'll look at a few examples of these. We won't do the integration and math and the calculus for all of them, right? We'll do it where it works out. Otherwise, we'll have processes in R to calculate probabilities, look up densities, generate random numbers, and things like that. That's what we're doing. Thank you. Yes.
I'm sorry, I was,
Oh,
I had burped.
Well, so this line one, so this was, it was written as A1 and A1 or A2 and A2. And so it might have included, so A1 or A2, A2. So it might have included all of A1 and that little piece there. So it might have included these things. And you and others also read it as excluding the overlap. So it was
Hey, Kelly.
kind of a funny
You
thing
actually
to
asked
happen.
somebody to take a picture of your.
You know, this one or
Friday.
those two. And so whether you just this one or just those two,
That's okay.
it was a decent image of it.
No problem.
Yep. Half the class thought that way, half the class thought that was inclusive. If it was inclusive, it would include those little parts in the middle as well, so. That's why it was here. Oh, no, that's all.
I'll send it to you.
already.
If it doesn't work, I'll just like,
Okay,
like, I'll send it to you.
Hey, thank you.
One copy at a time.
Yeah.
I'll do my,
Okay.
yeah, it's 2:30, right?
Yes.
I'll be there.
Okay. How are you?
Thank you.
I have to go over to lunch for like, fun day.
Yes.
Thank you.
Christmas party.
Right.
Well, also
So
like.
100, 700,
It's like, it's a
200,
3-hour
so-
lab of like,
Which is
I should
pretty
probably
hefty.
do something.
Or I plugged in.
I don't wanna be like in the middle of lab, just
Premium and.
right now.
Right. So this is 700 minus,
700 is the expected value.
right. I think maybe it's, if you reverse these two.
Well, they
So-
gave you the formula.
Yeah, so no, if somebody does, did I give you this formula, 700 minus, maybe it should be the
Well,
other
like,
way.
it's not 700, it's like minus 500 plus.
Right. So maybe it should be 500 minus X instead of X minus 500. Maybe these are backwards. The idea is that people have an accident, it's gonna cost $700. They have to pay $500 less. So I mean, the company is gonna owe $200 still to cover. But they want $100 profit, so people have to pay a premium of 300.
Yeah.
So that's what it should be, yeah.
Yes, that's what like I was like thinking about it, and so like God, it's just a bunch of shit.
Yeah. But maybe these things, if these two are reversed,
Okay.
then, or negative 100. So it's kind of viewing it, which is the cost of the